Good morning, everyone. Today we will start our NiTinol session, and it will end by almost at the end. But so it doesn't mean that the NiTinol is the only shape memory alloy we should look at. It only means that it exists in some semi-product components, so the engineers can easily use it. And if I'm speaking about NiTinol, I'm speaking about not only binary nickel titanium, but any kind of alloy which is derived from NiTinol, which could be titanium, copper, titanium, iron. Those alloy have slightly shifted transformation temperature, slightly different hysteresis, but basically you can apply the knowledge from the NiTinol also to those materials. And also, like even though NiTinol is beautiful, the researchers worldwide try to develop new alloys. The main reason is that NiTinol is somehow limited to temperatures below 100 Celsius, and for many applications we would require alloys at least which can be used at least up to 200 Celsius. So there is now all over the world a lot of activity in development. The alloys based on, we call it high temperature shape memory alloys with hafnium, zirconium, platinum added, and also so-called high entropy alloys, which are not already NiTinol, but they transform via B2 to B19 prime transformation, and it looks, and there is a good chance that such high in future such high entropy shape memory alloys can substitute NiTinol, because there is a problem with NiTinol. It has lots of kind of softness which we have to fight all the time, and these high entropy alloys are inherently resistant to plastic slip. So this is very nice development, and maybe in future the NiTinol will not be that important, but so far in these days it is. And so because of that I prepared this kind of introduction to NiTinol, which is a couple of slides with important information for you. Maybe when I was talking with some of you, like I should add some information maybe about the providers and so on. So I will a little bit update this information and give it to Professor Arokia. But here these slides are no. Yeah. So, as I said in the beginning, shape memory alloys are intermetallics. So the nickel titanium is typical intermetallics at 50-50 because it has a structure which is best imagined as two interpenetrating cubic lattices with nickel and titanium, and it has many, because being intermetallics, it has many advantages. So for example, like yesterday you have been present at the casting trial, and so if you try to cast intermetallics, if you have the composition of the material around 50-50, and if you melt it, it will always form intermetallics. So for example, if you mix together a nickel and titanium powder and do the combustion synthesis, it will tend to make the intermetallics alloy, not NiTi2 or others. Yeah? So the alloy inherently forms this phase, and the Martensitic transformation temperatures are typically, as I said, below 100 Celsius. It can be 0, it can be -100, -200, but it's not possible to have binary NiTi with AF transformation temperature above 100 Celsius, which is which is a problem for maybe for the actuation, because we are limited to low temperatures, and somehow, like here in India in summer, if you have 50 degrees, so actuation with 70 is not very convenient. Like in Czech, when we have 0 degrees, it is fine, but so it would be better to have an alloy with slightly higher, even for conventional application. And so this is kind of overview. I will speak in detail about some of these properties further. So this is a list of physical properties, again mainly for your convenience, so you don't have to search it in the internet for it. The thermal hysteresis is put here to like 30 to 50 degrees. Of course, I also took this information from physical tables. This is very funny because in fact if you have a NiTinol wire and if you do the superelastic cycling, you can decrease the hysteresis to 10 megapascal, which means that the inherent hysteresis of the material is probably much lower than 30 degrees. It can go down, but it is connected to, as I said, to this habit plane motion when we discussed yesterday. So when the NiTinol transforms from austenite to martensite, it has to solve this problem of the strain compatibility, and this needs some excess undercooling and overheating, and because of that you get hysteresis like 30 to 50. But if the material is cycled and trained, and then you do the thermal cycle again, you may have 20, even less, because the material already adapts to this transformation, and so don't take it so seriously, but don't expect to have NiTinol with hysteresis like few degrees or few megapascal. There will be always significant hysteresis. This is different with maybe NiTinol. If you want to decrease it, Nitanium, nickel titanium copper alloy works very well. It has hysteresis 10 to 15 degrees, because the copper affects the strain compatibility condition at the habit plane. So you can find in the literature the papers about so-called lambda cofactor, which means that by adding the copper to nickel titanium, the lattice parameters are changed in such a way that this compatibility condition is easily fulfilled. It's so simple.
So what is the strain compatibility? What does that mean?
Well, if you remember, I don't have it here. Yesterday I said that between austenite and martensite must be twinned. Yeah. So if you do it without stress, the material in NiTinol always have to go through transformation through this twinning, which is a little complicated process, because there are millions of twin interfaces. They have to be added to the material, and then the habit plane, this strain and shear in this strain is the same here and here. And the material does it by creating the laminate. This is the compatibility condition. I spoke about it yesterday, and I will be speaking again because it's very important in the end of this talk. But now and this depends on the strains. Here the strains depends, you can imagine, on the lattice parameters of the martensite. And with adding the copper to nickel titanium, you change the lattice parameters of austenite as well as in martensite, and it can basically do it almost single crystal martensite here and single crystal martensite there, nickel titanium copper. And then this interface, it makes easily the habit plane, and even under stress. So there is a famous paper in Nature by German scientist Hluba et al. And they show that if you have this nickel titanium copper, it's a thin film, they can run several millions of cycles, superelastic cycles, up to like 2 or 3% without any damage. So this would be our dream. Yeah, so you would have superelasticity with millions of cycles. The problem is that it works in their case of thin film with no defects, but if you want to make nickel, titanium, copper in bulk wire, it doesn't work. Yeah? But it's still much better than NiTinol. You know? And the reason for it is the effect of composition on lattice parameters. So the transformation strain, this is taken from the table. So here, if you make one cycle, it's 8%. But if you want to use it for some vibration damping, and you want something like 100,000, you have 4%. But this is pretty idealistic. I mean, to reach this level, it's not simple. Yeah, but remember this trend. Yeah, the more you want to cycle it, the less strain you have to apply. Then some physical properties, which I don't have to much discuss. Coefficient of thermal expansion. Well, it is not that different, first of all, and you can divide. This is defined always for single phase. It's like in physical tables. Then if you use it simultaneously, so you would have how many austenite, how many martensite. It is very important in this shape memory polymer composites, because you have the austenite wire embedded in the polymer matrix, and then you compare the thermal expansion of the wire in the matrix. And this is different. You know? So when you cool such kind of composites, depending on the CTE mismatch, you might get stresses here. So in those applications, this is very, very important. And the martensite has lower CTE.
Let's say we are making some device like the refrigeration cycle, which we have defined yesterday. Refrigeration cycle with the help of magnetocaloric
It doesn't play much role because the strains are very low. You know, transformation strains are 4%, and this is 0.002%. So it's very small strains. It doesn't. It plays role only if you are. Well, for example, you can easily, you know dilatometer experiments, yeah. So if you put a piece of NiTinol and you measure just dilatometry, so you will see the linear change when the martensite comes, yeah. So if there is no shape change during the transformation, you will detect the presence of the transformation from the change of the slope, which is this difference between the austenite and martensite. But you know, these strains are low compared to. So normally, when we make SMA models, there is a term for thermal expansion, but finally it's cut it, and no one is really use it in the model because the strains are very small. Specific heat, it's important for the any kind of calculation with heat absorption and irradiation. Sorry?
That was my question. Let's say if we want to find out the efficiency of that device, which is made with the help of magnet.
Yeah, then you need specific heat, sure.
So how can we sure that if we are using only one specification, not defining martensitic and austenitic, how we can define that this is the correct efficiency which we will use?
Well, I'm not expert in that. I cannot really answer. What I know is that if you want to evaluate, for example, the heat from if you do infrared camera measurement of the heat which is extracted, the specific heat is very serious, because depending on the specific heat, the amount of heat will be enumerated. Yeah. So I can imagine that in elastocaloric application this is the critical parameter, but you, as far as I know, you can't do much about it. This is this value, and there is no way to change it. You know. The electrical resistivity, so this is important. We will speak more about it. So the main for austenite there is one number. For R phase there is one number, but this is incorrect, because the resistance of the R phase is really changing with stress and temperature. I will be talking about it, but generally the R phase has high resistance. So you very easily detect this using some in situ resistance measurement, the start of the R phase transformation by the increase of the resistance. And so remember, R phase very high resistance, and martensite, you have here properly the spread of the resistance, because the martensite it never exists like a single variant. There are multiple variants, and the electric resistance depends on how they are oriented. So if it is, and also you have martensite, but it could be long and short. You never know whether it is long and short, yeah. But depending on the length, you have different resistance. So then you can normalize it with resistivity with respect to length, but still you will find the difference, because the way how electrons go through the lattice depends on the orientation of the crystallite, not only on the length of the wire. So you have here the spread of values for electrical resistivity. Then magnetic properties, I can probably. So we continue with Young modulus. So again the same thing. Yeah? The austenite has a modulus somewhere around 70, 80, 90. 80 is the mid. So, and there is no way to escape from it. So if you measure in some tensile test a lower modulus, there is some reason for it. Yeah? So either you don't measure correctly the strain, or you have R phase instead. It is linear, but in the material there is R phase transformation, or other reasons. So this is a very good. Like if you want to know that you have only austenite in your wire, just test the modulus, and if the modulus is around 80, you are safe, everything is fine. Yeah? So this is good. But then martensite, so in many tables you will find very low value like 20 to 40 gigapascal. And this is ridiculous, because like we know from steels that the martensite is the hard phase and austenite is the soft phase, and suddenly we have such kind of very low value of the modulus. So like there is again the same reason for it, because the martensite in the wire is not a single variant, but you have multiple variants, and you might have, if it is just cooled, so the variants are self-accommodated, it has some modulus. If it is compressed or deformed in tension, these variants reorient and you have different modulus. So for engineers this is crazy, I mean how the material can have different Young modulus, but it is very simple. It is the effect of texture on the elastic properties. Yeah? So the martensite is elastically anisotropic. If I pull it, I orient all the variants with one direction along the length of the wire, and my modulus become very soft. And that's the reason why it is soft. I will speak again about it in a little bit more detail, but what does it mean for the engineer? It means that the wire in tension will have anyway very low modulus. So there is a big change from 80 to 90 if you are loading the wire, so the modulus will change from 80 to something like 40. and this is not this is real. This is real. This is like, because if you orient all the variants along the one direction, you cannot continue that process. It finishes, and then it is real elasticity of the martensite. So if you have the stress strain curve, and this part is real elasticity of the oriented martensite, and the modulus is somewhere between 20 and 50. Strengths. This is very important, and we will talk a lot about the strengths. So okay, I took this from the table that the strength is 900, but the strength of the wire which we annealed yesterday at 900 Celsius was probably 500. So this is taken from the table, but by heating the NiTinol around 1000 Celsius, you would decrease the strength to 500. And work-hardened wires typically fracture about 2 gigapascal. So like you can have the material which has the strength around, normally if you buy the commercial wires, they would have strengths like 1600 megapascal, so very, very high strengths, and they can transform and they can actively work at such kind of high stresses. Poisson ratio, elongation to failure. I will talk more in detail about it later on. Machinability, very, very difficult. If you ever try to do the machining of a NiTinol bar, it's very, very difficult, because the knife, when you rotate the sample, it tends to bend. If it is not really rigid, it tends to bend under the knife, and it's very, very difficult. But now like the people already know how to do it. Specific speed is necessary, and then it can be done. Welding, very, very difficult because of oxidation problems. Corrosion performance is excellent because of thin titanium oxide, which always form on the surface of NiTinol. So even though you you completely polish the NiTinol, and then if you leave it at room temperature, after a few days there will be like tens of nanometer titanium oxide, which under the no stress condition provides excellent corrosion resistance to it. So everything is fine until you don't break the oxide by stretching the wire. Now, biocompatibility, so it has been in the last 50 years tested very much because of the medical implants, and so like after this 50 years, there is now very well developed the technology of, they call it surface finish, which means that only NiTinol which goes through this surface finish is acceptable for medical implants. And this surface finish means polishing and growing something like 70 nanometer thick oxide, which is homogeneous and good quality, and this is the surface finishing. And there are different steps and companies specializing in developing two surface finishing techniques. No, okay. So I will use this slide only to say the basic crystallography. So the austenite phase is B2 cubic with 0.3 nanometer lattice constant, and martensite here is monoclinic with such kind of lattice parameters. I would like to point out one very, 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 very important thing. Somehow in the literature, we use two kind of notations. You see here, normally if you have a low temperature, if you have low symmetry phase, how it is done is that A, B, and C are increasing from A to C. Yeah? But from some reason, mainly in America, people use C with this parameter. So then you will find two notations in the literature about the lattice parameters, but this affects everything. This affects yeah. So always, if you read an article about NiTinol, which is with transmission electron microscopy, X-ray diffraction, check what are the lattice parameters for Martensite, because you might be very, very confused. Yeah? So something which maybe I will now, later on, I will speak about 001 twins, 001 planes. In the other notation would be 010 planes. You know? So one has to be very careful on this. So, and then you have the R phase here. There is a orthorhombic transformation which occurs in copper-based alloy, and the difference between orthorhombic and monoclinic is only in this shear. Yeah? So if the monoclinic angle is 90, there is no shear like that. It's orthorhombic. Here it's monoclinic. But the difference is important, and I will be talking about it later on. Okay, so here I come to just normal standard NiTinol, which if you buy the wire, it would have such kind of property. So this is for superelastic wire. If with this composition, so most of the superelastic wires have this composition, and then if it is fully annealed, like yesterday we did at 900 Celsius, then you will have here transformation with about thermal hysteresis 30K, which is this one. But if this alloy with this composition is annealed around 400 Celsius for 1 hour, but anything between depends on the temperature and time, you will create this R phase. So this is the differential scanning calorimetry scan, and you see that now before this transformation start here, there is this peak. Typically this peak is bigger than this one, and so this is upon cooling, and upon heating both of these transformation proceed together. So we have seen yesterday when we bent this wire at the table that if there is only R phase, which is now, if you don't cool here, you stay with this red part, so you will have in the material only R phase. So the hysteresis is very narrow in temperature, but also in stress. And the narrow hysteresis in stress means that suddenly your Young modulus, instead of 80, becomes like 10 or 20. Eh? But this is that during when you are stretching your wire, the austenite to R phase transformation proceeds, and so you will completely change the elasticity of the wire. You feel it by, this wire, which is fully annealed, is very like a steel, and this wire is extremely soft. Yeah, so one can feel it by hands, very easily recognize whether you have the R phase or not. If you would anneal this wire again at high temperature, you will get back this behavior. And here, this is annealed at low temperature for long time, very long time. So you shift also the A temperature a little bit to the higher temperature, but the same thing one can obtain in memory wires. So here the R phase is around room temperature in superelastic wires. But if you do the DSC scan on some actuator wires like Flexinol, you will see that R phase can be around 40, 50 Celsius, and that's somehow different R phase because this R phase here, which is around room temperature, this is caused by small nanoprecipitates which are precipitating during the heat treatment. But in the memory wire, you don't have enough nickel because it has lower nickel content. So those precipitates are difficult to form, and so it has to be strengthened by cold work. So if you buy the memory wire, it always has some cold work in it, and the R phase is more due to the cold work. It's the same R phase, but the cause for it is in the defects, not so much in the precipitates, but more in the defects. And this R phase again is pretty stable around like 40 or 50 Celsius. So here in the list you will find some practical information how to detect and use the R phase in experiments. No. Čekaj, já musím klikat tady. I will, this is kind of overview. I will come to what is R phase transformation in detail talk. Just I don't know if today, but maybe you will hear a lot about R phase. Don't be. Okay, so this is the most famous diagram, which is very important to all of us, which explains why we can shift the MS temp. This is the MS temperature, and this is the composition. So this is 50-50, and if you go towards 51 nickel, you will decrease the MS temperature. This diagram is a little old. Recently, about 5 years ago, the German scientists measured in detail this dependence again, but the result is basically very, very similar. So we can shift the MS down wherever we want, but it doesn't continue here to the up. So if we go to the low nickel alloys, titanium rich, the MS temperature remains constant, so we cannot increase. Yeah. This is what I'm talking about.
Yeah. After that, some group, Japanese group, after some 5 years, I think it's 2020 or something, they have measured extremely low temperatures. What they are telling is, even for some compositions after 51 to 52, the Martensitic can be able to stable at extremely low temperatures, which is physical resistivity measurements, like physical property measurement systems. And the same thing in one, I think from Sunman group in KTH, calculation and all. What they have observed is, in phase diagram itself, they have given a description of B90 phase, B90 prime. And that's one actually, because they are considering an equilibrium Martensitic. This means no more a metastable phase, they are considering as the equilibrium phase. But I didn't see any experimental phase diagram, but they have given a description of it, and they have, in the phase diagram itself, at low temperature, they are putting a B90 as a stable phase.
Yeah.
You will note on
So you are talking about nickel rich alloys over here. Yeah. So this diagram shows from 50 to like 51, and then it stops, because with DSC, if you have NiTi 51, you don't measure anything. But it doesn't mean there is no martensite. Well, there are engineering application of NiTi-60 for some kind of friction and so on. The problem is that the more nickel is added, this intermetallic phase goes farther from its natural composition, and upon cooling it like doesn't form martensite on macro scale. But if we look with electron microscopy on nanoscale, we see basically a structure which is close to the B19 prime. This is the same stuff like and such alloy becomes very hard because dislocation cannot move in it because it's not normal lattice, and there are domains slightly misoriented everywhere. You know? So this is now people were thinking what kind of phase is this, because you cannot measure by X-ray diffraction lattice parameters of such phase because they will be extremely broad. You know? So this is it like you know, strain glass. You know what is strain glass? It's very well known concept in ceramics, and you know, and NiTinol, when you go up beyond 51 to 52%, become such kind of like a strain glass. So the better approach to discuss the properties of strain glass is to use the strain glass terminology, not the shape memory alloy terminology. So I'm not really talking much about it, but this doesn't mean those alloys are not useful. The funny thing is that upon cooling you don't get any martensite, but upon stressing you get superelasticity with quite good properties. You know? So, but simply because most of the NiTinol which exists in the labs is around this composition, there is not so much practical information about this high nickel NiTinol. But you are very, very much right. This is a modern type of research direction to investigate those kind of out of equilibrium alloys.
My concern is, in one of the calculations, they have given a B19 description at low temperatures, and they have included in the phase diagram. It is included in phase diagram. They are considering as an equilibrium phase at that temperatures. That being the case, but experimentally machine, as you told, experimentally observing that is very difficult.
Well, the problem with calculations is that if you do the density functional calculation, the B19 prime is not the equilibrium phase. They have some BO orthorhombic phase, and for the simulation to stabilize the B19 prime you need something. Of course, they calculate it at 0K, and we never measure it at 0K. So then there comes into the question. So one has to be careful with taking this information from the literature. But yeah, there is something interesting about the B19 prime phase, that the physicists who model the structure of materials, they never find it as an equilibrium structure. You know? And you are completely right that in some special cases they found it. But one has to be careful with taking this information from the literature, again because it's at 0K, temperature effect, composition effect, and so on. Okay, good. So then comes a question which somebody asked me yesterday, and which I feel very important. What is the best, because as I already said yesterday and today, the physical properties are changing with Martensitic transformation. So what we do, we measure the physical properties to detect the phase transformation, or in case of differential scanning calorimetry, we detect the heat which is generated. This helps us to tell when the transformation starts. But this is very incomplete information. You would like to know also maybe what is the structure of the austenite and martensite and other. You know? So, well, my answer to this question is that the best way to characterize whether I have martensitic transformation in the alloy is X-ray diffraction. Why? Because it tells you a lot of things together. It tells you the structure of phases you have. So if you polish your sample and make with lab X-rays, the measurement takes time, so you have to make few measurements. So if you make few measurements with a lab X-ray, you obtain such diffraction pattern, and they will clearly tell you I have at which temperature you have austenite, at which temperature you have R phase, at which temperature you have martensite. And moreover, in addition to that, the problem for most of the researchers is that frequently you have inside the wire austenite, R phase, and martensite together. So then you get a spectrum where all these peaks are together and they are not colored. So you don't know which one is from austenite, which one is from R phase, which one is from the martensite. Of course, there are two ways. The lab X-rays, they take information only from the surface of the specimen, so you have to be sure that the surface is the same as your bulk. So carefully polish. In addition, I myself, we did a lot of these neutron and synchrotron X-ray. So in that case, the information is taken from the whole volume. So you don't have to care much about the surface. And also you get, if you do like in situ loading, so you get the average information over all volume, not just the surface. So any trials to use stretch the NiTinol and use lab X-rays, you can have something, but you cannot really trust it, yeah, because the surface layer could be different than the bulk. You get the stress on the surface is frequently slightly different than in the bulk. But if you stretch 5%, it's okay. But still, you might have a different condition on the surface than in the bulk. So, these high energy X-rays or neutron experiments are more suited for in situ loading. And this is like my video which demonstrates how to animation, how to analyze, and I will be talking more about it later, how to analyze this diffraction pattern. So there is example of some typical diffraction pattern around 011 austenite direction, because this reflection is very intensive in X-ray. So you will, if you do the X-ray evaluation of martensite, you typically will see such kind of pattern. And then you don't know what is what, but in fact it can be analyzed with this animation. So whenever later on you will have this problem, please go and play this animation. So what does it show? So you have austenite, and this is the 011 austenite plane over here. It has some lattice spacing. This is very important plane in the crystallography of transformation. I will more talk about it. So if you do the experiment, this because of the Bragg equation, this lattice spacing will give you the peak around this position. You see there is almost nothing because this pattern is mainly martensitic, but there is some remaining austenite. And now we have something called lattice correspondence, which is the characteristics of the B2 to B19 prime transformation, and this lattice correspondence could be characterized by two relationships. So the 100 and 100M are correspondent, and this 011 could become in martensite either 001 or 010. Yeah? So what does it mean? So now I plot here the monoclinic lattice where you have the ABC lattice parameters, and I will try to find the lattice correspondent 001 plane, which is this one. So the C parameter is the longest parameter, you remember, ABC, C was the longest. So it is the longest one, and of course in D-spacing it shows up here. I had to change it because I also used the other notation before. Yeah? So now it is in proper notation here, and so because of the lattice correspondence, the intensity, if you have the austenite to martensite transformation from this peak, this will decrease and this will increase. Okay, but if I have the transformation which is upon cooling, also other variants may form, and into other variants, the 011 plane will change to this one, which has smaller lattice spacing. So it has the peak here. So now from one austenite I have two martensite peaks. In fact, there are two more because this 011 can, due to the lattice correspondence, can go to the 4. It looks like it is a little complicated, but now I associate it already 1, 2, 3, 4 peaks in this jungle, and I know from the crystallography that there are two more martensite peaks in this range, and now I have all the peaks here, and I can understand this kind of profile without any Rietveld analysis, just by considering the lattice correspondence between both phases. And so in the beginning we didn't understand very much. Yeah.
So you said that the D value is larger, then you have said it is getting bigger 002. So usually D is larger means theta should be less.
This is D spacing. This is the theta. If you put theta, it would be here. Yeah, this is D spacing. Yeah. So well, okay. Your question was very right question, because I am now just talking about it. So this pattern will appear here without if no stress is applied. Yeah. But if I apply this stress, and now I am look on diffraction on this plane, I will have mainly almost all variants will be extended. Yeah. So the variants which provide the shortening of lattice planes, which is this one, it will go down and this one will go up, and this is what we see in diffraction patterns of deformed martensite. And so well, I have found this in some old literature of Russian scientist. I even forgot his name. It was very complex, but he claimed that this method is good. Well, finally, the same method is introduced in any kind of Rietveld program if you introduce the texture into it. Yeah, but you don't see into it. If you play this animation, you see what are the so yeah.
So here lattice correspondence. Here we are talking about which martensite variant, B90.
I will be talking about lattice correspondence after that. Yeah, to explain. I know it could be a little bit puzzling for you, but well, in any martensitic transformation, the lattice correspondence is the basic. In steels, you know, they have this Kurdyumov-Sachs relationship derived, but this all reduces to lattice correspondence, which means how the austenite is rotated with respect to the Martensite lattice, and even though you have like depending on the type of the transition, you might have 6 or 12 or 4 different variants. The lattice correspondence is a single one. It's a single one. Yeah. So this is the basic law is, and you will, whatever the variant is, you will always find that this, if you properly index the austenite and martensite, you will always find this relation. But one should be very careful. You know, here this is the austenite and this is the martensite, and I am saying lattice correspondence. So the correspondence means that these planes are almost parallel, but they are not exactly parallel. There could be a little rotation, yeah, but almost parallel. So, and the lattice spacing, which was like 3, changes to 3.1 or 2.8 or something like that. So you can have this change. No.
Here we are like transforming 100 to 100 austenite to martensite, right? So this is twin martensite or twin martensite?
Now, well, twin means 2 different variants. So if I speak about lattice correspondence, I speak always about a single variant only. You know? So in both, the lattice correspondence is fulfilled in both martensite variants. But in one variant, it would be this, and in second variant, it would be that one. It's a little difficult. I will talk about this more in detail. But one thing is clear. You have a change of symmetry. This is high symmetry, this is low symmetry. So in high symmetry materials, you have like 6011 planes, while in monoclinic lattice, you have only 1001 plane. Yeah? There is no 100 is different, and 010 is different in monoclinic lattice. So you have always this, that from one peak, you have 4 peaks in martensite. This is a general rule for these patterns. Okay, and well, I just, all this is here mainly because I want to promote this table. This table, you don't see what is here, but you will get the foils, and we published this table recently in an article about TEM analysis of martensite variant microstructures, and this is the list of lattice correspondent planes like this 011 austenite, 001 martensite. So they are all listed here with HKL, and it can continue, but mainly these first are relevant, where this is the index of martensite plane, this is the index of austenite plane, this is the multiplicity, so how many of these will be created from one austenite. This is the lattice spacing of austenite, this is the lattice spacing, which cut? Martensite, yeah. You have better eyes than me, and I am here. This is the martensite lattice spacing. This is the austenite lattice spacing. This is the, as I said, they are not exactly parallel. There is some kind of misalignment, and this misalignment is perfectly seen in TEM images. Yeah? So in TEM images, you have a diffraction pattern. You have a spot from the austenite, and spot from the martensite is slightly besides, and this rotation means you have misorientation of planes. So you have this, and then you have, because if I have this lattice spacing in austenite and this lattice spacing in martensite, what does it mean? It means extension. So this extension strain or compression strain is here. This means this table, the compression is in red, this is in blue. So for example, like if you look here, this one, which is 10 minus 3, will give you maximum deformation in tension. And really, if you look into the diffraction pattern, the 10 minus 3 reflection will be maximized because all variants are oriented into this direction. So this is something which is not normally in the you will not find it in the textbook. It is our result, but we use it very beneficially in analyzing the X-ray diffraction and TEM diffraction, as I will show later. So it was published in Acta Materialia, and you have this table in these slides. I will maybe come later on to it.
Tension and compression with respect to austenite. So an austenite crystal is either compressed or tension. So you have a ball gap, right? Ball gap is reference to austenite.
Now, this is the austenite cube, and I have, for example, this is the the very first one is the 011. This is the 011 in austenite, and the corresponding is 001 as I have shown in martensite. Okay, so this is the austenite cube, and now the martensite lattice, which is a strained austenite, basically, the bane strain, shape strain is applied, is rotated in such a way that the long 001 axis is aligned with this 011. So your question is basically irrelevant. I mean, you have one lattice, second lattice, and this is about the rotation, about how it is rotated. So it is extension along this direction. If I have these planes, so it's always along this direction. So if lattice spacing is larger, I have extension like 11%. And I will show a little bit later on that this change from austenite to martensite, it's actually expansion along one direction and shortening about two directions. So this is logically out. Only from this you can understand that if I have a NiTinol, I can obtain more strain in tension than in compression, because the shape strain from the cube is the martensite becomes long in one direction and shorter in two directions. So and this table is the result of this process. I should say one comment how this table was calculated. This table was calculated just by having austenite and having this lattice correspondence, which allow to rotate the martensite maybe in 4 ways, four ways, and this gives you the possible strains which you can obtain from 1001A into the 4 martensite patterns. So frequently here you would have this color, yellow, this is the austenite, and all of them are typo 110, number 011. But here the martensite reflections are different, because from one set of the planes I get 4 set of the planes. This is the colors are here the same austenite lattice plane. This one is 121, the red one, and so on.
What is the explanation for the normal transformation
Well, strain is a tensor, so we still can calculate, if this is the lattice spacing, this is the austenite, this is the martensite, this is so I can calculate the strain in the normal direction, but also shear. So somehow we calculated also shear, we added it here. I don't really know what kind of meaning it has. We cannot measure it. So this is the tensile strain, compression strain, and shear strain. So for example, here there is no shear strain, but here there are some shears added. Yeah, this would be important if this like you want to simulate how the atom position change during the transformation. So you need to know these shears. Okay. Good. So this is the end of some kind of overview of NiTinol physical properties, and I included here basically because you had many questions to what is this strain compatibility and this habit plane, and because we were working on that recently and I found it quite interesting, so I added the few slides about this one. So this just explains why it is, because recently it has been well, not only, okay, we are studying the plastic deformation of Martensite. So as I said, the plastic deformation of Martensite occurs at high stresses beyond the yield stress, but unfortunately not only that, it also occurs if you use the wire in the range where only transformation should be. So if we do the superelastic cycle at 500 megapascal, the response is not completely stable. Aha. Tak to jsem neměl. No. Good. This is the contact. There is some problem. I will have sometimes this problem. Please be patient. I don't know what's beyond. There is some contact problem with the HDMI connector. So what happens is, and you will find it with almost all any experiments you do, if you do superelastic cycling, it's unstable, the plateau shifts down and you have this unrecovered strain. If the stress is high, like 800 megapascal in this curve, the unrecovered strain could be 1%. If the strain is lower, it could be 0.1%, but it is here. And what is the reason for that? The same thing in thermal cycles. If you do cooling, heating under stress, if the stress is high, you will never recover completely upon heating to the same strain. So what does it mean? This means that some sort of plastic deformation accompanies Martensitic transformation. And so we did a lot of systematic research on this, and we really found exactly that. So the plasticity occurs when the transformation proceeds. In other words, if I have the austenite and I load it to 1 gigapascal 20 times, there will be no plasticity. At high temperatures, no plasticity. If I have the martensite, I load it, unload, cool, and you do shape memory effect. So I load it to 1 gigapascal, unload and heat, no plastic deformation. But if I perform a cycle when it transforms under 900 megapascal, very big unrecovered strains. So this plastic deformation occurs when the transformation proceeds. And that's a problem, because you cannot get rid of that, because you want to utilize the transformation and the plasticity comes along. So what?
Maintaining the temperature below austenite start, right? What is the temperature start?
Okay, this is just the figure which shows the superelasticity at probably quite high temperature, so the stress is very high. You know? We normally, you don't use 900 megapascal, it's too much.
What are the temperatures in those rates like that?
It's not set. I estimate if this is super elastic wire, so I estimate like 100 Celsius.
Okay, above air.
It's It's all It's about 100, but it doesn't matter. You know, if it would be at room temperature, the unrecovered strain would be here. You would not see it, but it will be there. So I wanted to show that it is here, and the same with high stress here. And so, like I said, that we are striving for NiTinol, which can be used at high temperatures, and we want to shift the AF temperature higher. But it helps a little bit that if you have higher AF temperature, you might have super elasticity at 100 Celsius at lower stresses. In that case, it helps, but this problem with plasticity accompanying transformation remains. And it will be here always, and it will be here at any kind of high temperature shape memory alloy in nitihafnium, it will be there. So we have to understand what is behind. And so we don't really understand what is behind, but we know how it looks like. In this case, this is the stress and temperature. This is the stress temperature map, and we try to evaluate these unrecovered strains, and you see how quickly when you increase the temperature and when you increase the stress. So, I mean, it's better not to speak at high temperatures or high stresses because it's related. The stresses and temperatures at which transformation proceeds are related by this Clausius-Clapeyron equation. So you will find out how quickly it increases, and this increase basically kills your superelastic or actuation applicability. So you cannot use it at to be on the safe side, you have to be here somewhere here. And so the problem for scientists is to find out the origin of this phenomenon.
So this is for a single cycle. What about repeated cycles?
Well, repeated cycle, it would this is the problem. You would come here, and it will come up here, and like that, and it's accumulating, but slowly saturating, but accumulating, and it will be like the saturation curve would look like this. So here you have thousands of cycles with some constant slope. There will be still some small increment. Of course, if the temperatures are low or stresses are low, it would look like more flat, you know? But it will still be there. So, yeah.
So this right side curve, stress temperature, unrecovered state. So this is for how many number of cycles?
This is a specific experiment in which we measured it. We did what we did was that we took a NiTinol wire and applied like 10 super elastic cycles or 10 thermal cycles or different kind of cycles, but always 10 of them, you know. But you can plot the same image for just one cycle. But if you do it for just one cycle, because people know that first cycle is different from the second one, they will not believe you. So that's why we measured 10 cycles. After 10 cycles, you, like I said, there is this stabilization, yeah? So this knee over here, for most of the alloy is around 10 cycles. So in the first 10 cycles, it increases quickly, and then it goes slowly.
So we can say that whatever the unrecovered state there which is getting accumulated every cycle, after 10 or 15 cycles, that amount will be very less.
Yeah, much less, no, not very, but much less, no. So it's good idea before you use the wire for superelastic application to make 10 cycles exactly with strains you want to use, and no more. If you do more, it's maybe redundant, but same type, same strain. You know.
So what can be the reason for this unrecovered state?
I will be talking. That's the next part. Yeah, we had some theoretical ideas about it, but I don't want to spend. Because okay. As I said in the literature, this article in Nature by Chluba et al. About the cofactor is kind of influential, and many people believe that this is the case. So what they actually predict is that if you add copper to NiTinol, you will change the lattice parameters and you will make the strain compatible at the interface. But in fact, the situation is a little bit different, and we now believe that even in NiTinol, when stress-induced so far I have been saying that austenite transforms to twinned martensite. But is it true? This Chluba says if you add copper, you can do it without that. We have the idea, which was not yet published, but it is in two figures, that you can achieve the same with adding little plasticity. Yeah, so in NiTinol, you also transfer between austenite and single variant of the martensite, but without having fulfilled completely this compatible condition. Because the calculations which are done for no stresses. But under stress, your cubic is changing into the orthorhombic shape because elastic deformation expands it a little bit. And also, you might have some plasticity. And every experiment tells us that at high temperature we have plasticity. So it's appointing to consider some kind of plastic deformation which can be added to the transformation. And this idea is shown here. This is austenite and this is martensite. And as I said, this simple animation shows how the blue martensite lattice is created from the austenite. So this is the 110 plane. So you have some shortening here. You have expansion in this direction, and you have monoclinic distortion. This animation, it will play in your slides when you have it. So for me, this is the best way how to imagine what is it the cubic to monoclinic transformation in NiTinol. And these are the lattice parameters, and you also now this is only the kind of shape of the lattice, but in fact the lattice is made by atoms, so you have to know the position of the atoms. So here this is the austenite with nickel and titanium atoms. Titanium is in red, nickel in blue, and this is how it's converted into the martensite. This is the animation which you have seen before, and this is the projection, but now you see the position of the atoms. So if you the exact position of the atoms here is not so easy to imagine only by this shape strain. You have to take into account some other deformation to really obtain the structure with atoms in position where they should be. And it is important, like if one does the analysis in TEM, to consider the proper atomic positions. And there is a jungle in the literature. Most of the people do not consider the atomic positions at all. Then they can index the pattern, but they have no ideas about the intensities. So this scheme here shows the current level of understanding how are the atomic position. It is published in this article. And now I said that we want to come with a theory which says that in NiTinol you transfer between monoclinic, between single lattice of austenite, single lattice of martensite, which is actually such kind of transformation would be prohibited by this PTMC theory, which requires here the twin laminate. But we say instead of twinning, you have slight elastic and slight plastic deformation. And if you have this, well, okay, you even don't need. This is the calculation, as I said before, if austenite changes to the martensite, so I can calculate in which direction I would have which strain. So this is the calculation in monoclinic lattice, which says that the major elongation is around the -103 direction. So, like, remember only this simple fact that you have austenite and you have martensite, and martensite is long in one direction, and this is -103, and this gives such kind of orientation dependence.
I have a question.
Yeah.
So, the strain which you have written down in the previous slide. So, basically the elastic green strain is F transpose F minus I.
Yeah.
But what is the specific reason you have just written out F transpose of F?
Okay. I think this gives the same value eventually. If you add F transpose with F and divide it by 2 minus invariant matrix.
F transpose times F. That is the, if you...
No, this is actually the product of the gradient of F is the transformation gradient, deformation gradient, and with this you can get the okay, we are interested in the maximum elongation along some particular direction, which is this epsilon. You can obtain this epsilon, and you can have it along either austenite or martensite phase. And here it is plotted with respect to martensite phase. Normally in the literature you will find it always with respect to the austenite phase. Because why? Because people have this laminate on the other side, but we don't have any laminate. I am now talking about change from austenite to single variant of martensite. You remember most of the experiments which I shown so far kind of suggest that the martensite lattice is oriented in one particular, even in polycrystalline state. And so that's why we plot it in the austenite in martensite coordinates. So this is the equation for calculating it in martensite coordinates. Okay, so here it is. There was this animation which showed the change, and here it is plotted just 2 sections, and you see here this small misalignment. This small misalignment which is here, particularly this one here, which is this epsilon 2. This is this problem which the Chluba had, and which they solve by changing the lattice parameters in such a way that this red and blue are equal. In our case, they are not equal. And in our case, in NiTinol, they are not equal. So, and maybe I should also say, Using this figure. Imagine this is the 011. This is the 011 lattice plane of the austenite, and so it becomes, we call it basal plane of the martensite, and so this is like one twin, and symmetrically here you can have second twin. So from 011 plane you have two variants, and this view is suggested here, that I have 6 011 austenite planes and two variants out of that. So together there is 12 martensite variants which can be created from one cube. And you can describe this by matrix equations, and you can work with those kind of strain gradients in estimating the strain. So the same table in different kind of versions you can find in many articles. I believe that this is one of the most convenient types, so you will find it in the slides. Okay, this I shown. I already said. So the problem is how to equalize these strains in O1 along the O11 plane. This is when it is plotted in with respect to the austenite. So with respect to the austenite phase, I have here this and this, which during the particularly this third principal strain and first, this very large mismatch is basically already taken care by the Bain strain. So along this direction, the martensite is oriented in such a way that there is no strain mismatch. The only problem remains with this second principal strain around about 3%, but 3% it's a lot for elasticity. Elasticity can make 0.5%, not 3%. So but when we look into the, so we still have this 2% which no one knows how to explain. But if we look by electron microscopy, high resolution electron microscopy, we clearly see interfaces which are between definite austenite and definite martensite. We see them, they exist. So the theory says it cannot exist, but every experimentator, if they look into the material by TEM, he found they exist. And somehow, so this was published in this article, but you will find it in many others. One thing is interesting, that if we find by high resolution these interfaces, so if you look, this is the interface, and this is the 100 in B2, and this is the 001 in, and you find some kind of mirror symmetry. The 100 is not parallel to the 001 because you have only one. So, but still there is this mirror symmetry, and we will find this mirror symmetry repeating many times then. So this is sort of evidence that when the nature created this interface, the strain compatibility was the key rule which had to be respected. So at first we consider like two phenomena which may diminish this strain incompatibility. First one was elastic deformation. So if I have elastic deformation, I load the crystal maybe to 500 megapascal. It's not cube anymore, it becomes orthorhombic, and I can load equally the martensite, and because the martensite is elastically anisotropic, it will provide different strain. Yeah? Yeah, it's time. So basically, the elastic strain can help to minimize this. And the other possibility is to rotate the habit plane, because now this lattice could be any kind of lattice. So we did the analysis, we rotated the habit plane, and simply found that for around 112 plane, you will find you will get a minimum where the lattices are compatible. So I will go very quickly to finish this lecture. So what comes out of this? Yeah? So in the literature, you will find that when the self-accommodated martensite is formed from the austenite, so you have such kind of laminates with the habit plane. So the PTMC theory predicts that the martensite twins will create the laminates based on the habit plane on 111 martensite plane, which is here. So this is probably, I don't talk about it because this is very well in the literature, this kind of triangular symmetry with habit plane variants made of type 2 twins on 011 martensite plane. This is observed in single crystal, this is observed in polycrystal with large grain size, but it is little bit complicated, and we have been investigating in last 5 years the wires with very small grain size, which are most of the wires which we use if we don't put them into the 900 Celsius. So those one which we buy, they have very small grains, and here there is also laminates, but different kind of laminates. The laminates which can be observed in tooth materials are formed by such kind of families of 001 twins. 001 twins are these two twins because they are on this is 001 plane. You know? So these twins are here, and this is the 001 twin laminate. This is another 001 twin laminate, and they combine together create the habit plane. This is not really known. You can find it in like 10 years ago in papers by Weitz from Vienna in Austria. He first came with the observation of, but he didn't observe this habit plane. So he only proposed it. But we have observed later on to the habit plane and kind of confirmed this conclusion that there are. So the conclusion is, and it's not, it can be easily accepted, that if you have a single crystal of big grain size, you can have laminates which have a spacing maybe 100 nanometers because it's big. If you have a grain which is like 50 nanometer size, then how to put laminate with 100 nanometer into the 50 nanometer dimension? It is not possible. So the microstructure must be much finer. And for NiTinol it's very easy to make these 001 twins. I will show you by electron microscopy, every 5 nanometers there could be such kind of twin. So for NiTinol it's very simple to make such kind of microstructures, but then the habit plane is constructed in a different way, but it can be constructed as well. So there are two kinds of self-accommodated microstructures which can exist in the NiTinol. I will speak more in detail about this later on, but I would like to close this part with this idea and have a small break. Thank you.